bit for the upcoming test on 4, 5, and 10. Okay, but the best way to learn how to use NMR is to interpret spectra, and there is a combination set of spectra online on Blackboard. But they're combination sets in the sense that you have an infrared, what we call a low resolution mass spectrum, and then a hydrogen NMR and a carbon NMR. And we are studying NMR separately right now. We haven't looked at mass spec and infrared, but I thought I would include that and just tell you basically what would be read about this compound from the infrared and the mass spec. It's relatively straightforward and simple, much easier to read infrared and mass spectrometry data than NMR data. And when we quickly get to infrared and mass spec, it'll help you understand it. This is an infrared spectrum of an organic compound right here. The only thing that's artificial are these two vertical lines, which I drew in with a pencil. But an infrared spectrum looks at how an organic molecule absorbs energy in the region of the electromagnetic spectrum that we call the infrared region. You know that the electromagnetic spectrum is a very, very wide energy spectrum. This is where light is. Optical light is a particular region within this wide electromagnetic energy spread, and spectroscopists have sort of carved it up because you can get different kinds of information by exploiting how a molecule reacts to electromagnetic radiation in different regions of the electromagnetic spectrum. So we actually have, to break it up, the Einstein equation relates the energy, actually in joules, to the frequency of electromagnetic energy. The highest frequency that spectroscopists work with is gamma ray, and we have gamma ray spectrophotometers. You may have heard of a gamma knife that surgeons use for supposedly bloodless surgery. That's using gamma rays actually to slice through tissue. But gamma ray spectroscopy is not a routine tool for organic chemists. After gamma ray, we have the X-ray region, which of course you're all familiar with in medical terms, but actually in science, there's a technique called X-ray diffractometry that shines an X-ray beam through a crystal or a powder. It has to be a solid, and the way that the molecules diffract the X-ray beam gives you information about the three-dimensional structure of the molecule. With computer simulation, this technique can actually show you the atoms as spheres and how they're next to each other in the molecule. This has traditionally been the main tool for three-dimensional imaging of molecules. If you go to the protein data bank, for instance, you will see a large collection of X-ray crystal structures of protein. After X-ray, you get into the ultraviolet region, where molecules absorb energy by electronic transitions. That is, electrons jump from lower energy levels to higher energy levels. It's a fairly energetic process. For instance, typically the wavelengths in the ultraviolet region are strong enough to break carbon-carbon and carbon-hydrogen bonds. fact, in many parts of Europe and even some parts of the United States, ultraviolet is used to disinfect drinking water. And if you're a biologist, you're probably familiar with UV sterilizers, et cetera. They can obliterate organic molecules because there's so much energy there. But if you back off a little bit, you can get information about the electronic character of an organic molecule in the ultraviolet region, which spreads over also into the visible wavelength region. And most spectrometers in this region are called UV-Vis spectrometers. In the visible wavelength region, you also get electronic transitions and electronic information. The reason for the split there is because the visible region has significance, obviously, in terms of vision. Your eyes respond to electromagnetic energy in the visible wavelength region, and the whole phenomenon of color has to do with absorption in that region. Any substance that's colored, other than plain white, is absorbing light in the visible wavelength region, because your eyes are tuned to a certain energy balance in that visible wavelength region. Basically, sunlight is interpreted by your brain as colorless, and if you alter that energy distribution, because this is a range of frequencies, to take out some of the energy selectively, then your brain will turn that into some type of a color. So if it absorbs in the blue wavelength region, you see the complementary color in the reflected light as yellow. After that comes the infrared region. Now, this is lower in energy. Gamma ray is the high end, and now we're getting to lower and lower energy. The frequency of the electromagnetic radiation is dropping. So again, we're talking about a beam of electromagnetic energy that moves at the speed of light. So the speed or the velocity of the beam is always constant, but the wavelength changes, and so the frequency and the wavelength are variable, but related. High frequency means short wavelength, low frequency means long wavelength. You're all familiar with infrared radiation, any type of electric heater that you might have at home, for instance, or a hair dryer that's producing heat from infrared radiation. Now, infrared is actually invisible. People think it's red, but it's actually not picked up at all by your eye. What you're picking up is a little bit of spray light in the visible region, because you can't filter these regions exactly on the edges. So an infrared beam is colorless. If you stand in front of a fireplace, the heat that you're feeling, you might think is just due to hot air coming at you, but it's due to radiation. Radiation from the flames is interacting with molecules on your skin and causing them to vibrate. Infrared energy is vibrational energy. It causes bonds in molecules to vibrate. The best model for a chemical bond is a spring. Picture, if you've had physics in high school, you know this. You go through all these problems where you have a spring attached to two masses, or one mass and the other end attached to the wall, and that spring can vibrate. You're all familiar with vibrating strings, like on a guitar or a violin or a cello, etc. That type of thing occurs in molecules where the bonds, which are always vibrating slightly anyway, pick up energy from the infrared region and start vibrating with a greater amplitude. Same frequency, but larger excursion. You know that if you take a spring and you stretch it a little bit and let it go, it will oscillate with what's called its natural resonance frequency. If you stretch it really far and let it go, it will still oscillate with the same frequency, just the excursion will be wider. So a chemical bond is like a spring, or a string on a guitar or a piano, lyre, etc., it has a particular resonance frequency that is really created by the masses of the atoms on the two ends of the bond and the nature of the bond itself. Again, if you had physics with springs, you know the springs have what's called a force constant, and there's a equation called Hooke's law that governs that vibration. Same thing with springs. So a molecule is like a big collection of tunable strings, like a violin. And when infrared radiation hits the molecule can absorb energy from the infrared beam, but only when the energy exactly matches the resonance frequency of the bond. So it is a resonance phenomenon. And in the infrared spectrum, the y-axis is percent, you can't read it, but that's percent transmittance of the infrared beam through the sample. So if the sample isn't absorbing anything at all from the beam, you have 100% transmittance. That's why your baseline is actually at the top. So it's like an NMR spectrum upside down. Absorption is signified by a downward swing or an inverted peak, like this. These peaks here, this peak right here is an absorption at a particular frequency. There's a little bit of spillover because this resonance thing is not perfect, and there are lots of, well, like if you pluck a guitar string, the other strings will start vibrating slightly also because they pick up harmonics and overtones. The same thing happens here. So peaks get a little bit broad, but you can see they're relatively sharp. And these represent, this is basically a frequency scale here. It represents absorption of energy. The lower the peak goes, the more energy was absorbed. And where the peak is characteristic of the chemical bond. So if nothing else, it's like your signature. It is a unique trace for this molecule. No two different organic molecules have exactly the same infrared spectrum. There's a lot of stuff in that spectrum. There may be similarities between two similar compounds infrared spectrum, but never complete match. And so you could do database fingerprinting with infrared very easily. Infrared spectrometers in this modern day come with search algorithms and large databases. So if you get an infrared spectrum, you can search the database the same way that the FBI would search a fingerprint database or a facial recognition database looking for a hit. Now that's not interpreting or reading the spectrum, that's just computer matching. With some experience, you can actually read things in the spectrum because suppose your compound's not in the database. Same thing that happens, on NCIS when they're looking for somebody and they're not in the facial recognition database. What does it do? Well, they would lead you to believe it does nothing, but it doesn't. It puts up the closest space it can find. In fact, it puts up the 10 or 20 closest spaces it can find with complicated statistical data that you're supposed to interpret to lend some validity or not validity to that facial recognition. And that's why people who run universities are torturing you by making you take statistics, trying to help you. Statistics are just a natural and inescapable reality when you're looking at data. Anything that comes from a database has not a yes or no answer, but a probability of being correct. And you have to understand various statistical parameters that either support or degrade that validity. Okay, so this spectrum here could be interpreted by eyesight, and one of the things that you look for in infrared is the presence of oxygen. Now you can bet your last nickel that this organic molecule, it's organic, contains some carbon and hydrogen. The next big issue is, does it contain an oxygen? If it contains an oxygen, there are only 3 flavors of oxygen: OH, C-double-bond-O, and COC. The alcohol oxygen, the carbonyl oxygen, the ether oxygen. The one in the middle is the most complicated. Because you know that carbonyls come in aldehydes, carboxylic acids, esters, amides, ketones, etc. Lots of different types of carbonyl compounds. But if you can tell simply whether there's oxygen or not, you've gotten 90% of the valuable information out of that spectrum towards interpreting what this is. Now, I'll tell you that this peak right here is C-double-bond-O. C-double-bond-O comes right in the middle of the spectrum. And so that's a dead giveaway. This compound unquestionably contains a C-double-bond-O. If there were no peak, and C-double-bond-O, well, we'll go to the scale now, there's a range where it appears. It does vary a little bit. So you look at this little window that you know is 4 C-double-bond-O. If there's a very strong peak there, that's a C-double-bond-O. If there's no peak there, you definitely do not have a C-double-bond-O. The OH would appear, and I'll show you one in a minute, up in this region right here, and the COC, the ether, appears down in this region. So I can look at this infrared spectrum and say it contains oxygen. You always use what we call Occam's razor here, which is that the simplest possible explanation is the one you go with first. So I'm assuming there's 1 oxygen. That's more probable than 2 or 3 or 4. There may be 7, but the probability is not there. So I'm going to come down now to the mass spectrum, which is right here below it. And in this mass spectrum, you see there's a line there on the far right that's labeled 134. Right there. This is mass right here. 25, 50, 75, 100. You can ignore all of these lines here. When you interpret mass spectra, you go all the way to the right to the peak with the highest value on the x-axis, not vertically, but horizontally. That is an even number, 134. And that's written in by hand, but that's what someone would interpret. That becomes the molecular mass for this compound, 134 atomic mass units. Now, when we get to mass spec, you'll see also that there's an easy way to tell whether there's any chlorine or bromine present. Don't need to go into it, but by the appearance of that peak furthest to the right, you can tell whether there's a chlorine or a bromine, and I can tell that there isn't. So I know that this formula doesn't contain any chlorine or bromine. It does contain oxygen. I'll assume it's 1.
Why did you say
It's something that you look for in the mass spec. It has to do with the large isotopes that those atoms have. Chlorine has 2 big isotopes, and so actually you see 2 peaks, almost the same size, and same with bromine. Nitrogen can't be here, or probably isn't here, because if a compound has 1 nitrogen, this number is not an even number, it's an odd number. You're not going to see very many nitrogen-containing compounds yet. But there's something called the odd nitrogen rule in mass spec, which is that the mass for the whole molecule has to be an even number, unless it contains an odd number of nitrogens. 1 or 3 or 5. So I'm assuming there's no nitrogen. It's just a CHO compound, which is, 80% of all of the naturally occurring organic compounds contain nothing but carbon, hydrogen, and oxygen. That's a pretty safe bet. Okay, so 134 and 1 oxygen. Now, oxygen has a nominal mass of 16. The main isotope of oxygen, it really has just one significant isotope, O16. So by subtracting out the oxygen, I'm left with 118 atomic mass units for carbon and hydrogen. So what's the maximum number of carbons I could have? Carbon is 12, well, H is 1, carbon is 12, oxygen is 16. Can I have 10 carbons? No. I wouldn't have anything left over for hydrogens. So if we back off to 9, that would be 98. 9 times 12 is 98. 108, I'm sorry. So if I have 9 carbons, that leaves me 10 mass units left over for hydrogen. And I already assumed I had 1 oxygen from the infrared. So that gives me a molecular formula of C9H10O. Now, careful, that's not the structure for the compound. That's just how many carbons, hydrogens, and oxygens are there. Lots of structural isomers are possible in this case. But certainly an easy thing to do is calculate degrees of unsaturation. As you remember, you just ignore oxygen. And if this were totally saturated, it would be C9H what?
20.
Totally saturated, 20. So how many degrees of unsaturation do I have? 5. I think I issued a warning last time about 4 degrees of unsaturation in a small molecule, indicating probably a benzene ring, because a benzene ring all by itself soaks up 4 degrees of unsaturation. 4 out of the 5. So I have 5 DOUs, and I know I have a C double bond O, so that's obviously the 5th one. Now that's 7 out of my 9 carbons. And you notice this is like a puzzle, and I'm weaving my way through it, only extracting the easy information, and I keep moving. So I'm not going to try to figure it out at this point. I'm going to look at my NMR data. Because once you get down to a formula and some other information, and it's really an issue of how do you put all this together. That's 7 carbons. I've got 2 more carbons to go, and I have to have at least 1 substituent on this ring. We assume it's 1. That's 5 hydrogens out of my 10. So I've got 2 carbons and 5 more hydrogens to account for. The HNMR is best at settling this issue of the finer details of this structure. So let's just go down to that. Okay, the one on the left is the HNMR, and the one on the right is the CNMR. Okay, if you look at the HNMR, these are the integration values four things in HNMR. How many resonances do I have? Tells me how many chemically different types of hydrogens, where those resonances are, the chemical shift tells me something about the types of hydrogens they might be, the areas under the peak tell me the relative numbers of hydrogens, and any spin-spin splitting that's present tells me how those hydrogens are sitting in the molecule in relationship to each other. Okay, so, by the way, I'm supposed to have 10 hydrogens. Check to make sure that adds up. So all of this area has to account for my 10 hydrogens. So you can see it's exactly as written, 3, 4, 5, 6, 7, 8, 9, 10. 5 hydrogens on a benzene ring, right here, between 7 and 8. Don't be distracted by the appearance of the peaks, splitting into 2 different resonances with lots of spin-spin splitting. That's typical for a benzene ring. I'm happy to know that it's just a monosubstituted benzene ring, so that's 6 of my 9 carbons. The carbonyl is a 7, and here are my 2 other carbons with hydrogens on them in a 3-to-2 ratio. 3 hydrogens is always a CH3. 2 hydrogens is always a CH2. Almost always. And you can see that that's a triplet quartet pattern. So what does that mean? They're next to each other, right? I have a monosubstituted benzene ring. So this is fixed. Now there is another possibility here. Actually, there are several other possibilities. Now there may even be more, but if you restrict yourself to a monosubstituted benzene ring and the carbonyl, these are 3 obvious structural isomers that could be this compound. And they're all consistent with the infrared data and the mass spec data. They all have the molecular weight of 134. They all have the same formula. They all have the C double bond O that we picked up in the infrared. How does the NMR pin this down? Yes? Right, that's the whole idea here. How many different hydrogens, the spin-spin splitting, all of these little details are intimate details about the hydrogen geography in this molecule. Those are bits of information that are mapping the hydrogens for you. So, this one in the middle, how would the CH2, it does have 2 hydrogens and 3 hydrogens in 2 different resonances, but why isn't that a good choice? Right, they'd be what? They'd both be singlets. I have a 2 hydrogen singlet and a 3 hydrogen singlet. It's only the spin-spin splitting that eliminates the one in the middle. The one on the right would have spin-spin splitting, but it wouldn't look like a quartet and a triplet. You don't even need to think about what exactly it would look like. You just know that it can't be a quartet and a triplet. And aldehyde hydrogens are pretty easy to pick off because they're at around 9 parts per million, a very bizarre position in the NMR spectrum. We don't have anything out around 9. So if you look at the carbon spectrum, it's really just an afterthought. And that's the way I often use carbon spectra, just to confirm, so I'm not missing something. Based on carbon, how many chemically different carbons are in this molecule? Assuming this is the right one. No. Nope, it's going the wrong direction. Well, clearly it's more than 3, because that doesn't even count the benzene ring. How many chemically different carbons on the benzene ring? Right. Now the ring is symmetrical, but you have what we call an ipsocarbon where the substituent is, and then a pair of so-called orthocarbons, and then a pair of twin metacarbons, and then a paracarbon. So there are 4 different carbons on the ring, 5, 6, 7. There are 7 chemically different types of hydrogens. Now you don't actually see 7 here because of the compression of the scale, but this is the CH3, this is the CH2, this is the C double bond O out here. And then these are the peaks on the ring. This big peak is actually 2 that are very close to each other. But if you expanded the scale, you'd see that there's actually quite a big separation between them visually. So it's a puzzle. You put the pieces together. Now this is done partly by using databases, because not only does an infrared spectrum have that fingerprint quality, but so does a mass spectrum. Let me go back to that mass spectrum.